Okay, time to switch off your cell phones again. It's my great pleasure to introduce a very good colleague of mine, very good friend, I would say. We go back to '99 when I was running JET, and Ambrogio did his first experiments on plasmas in JET that I was running. Since then, Ambrogio made a very, very steep career. He became full professor in Lausanne in the end and the head of the Swiss Plasma Center, which was opened some time ago, I think 2 months exactly. They had an opening event just like this one. I think Ambrogio is going to give us a very nice bird's eye view on fusion physics, fusion instrumentation, and I'm really excited to have you here, Ambrogio. Go for it.
Thank you very much, Marco. It's a great pleasure to be here. I will try to give you some highlights of what we do in plasma physics for what I call burning plasmas. I will define what I mean by them. We have quite a few similarities between the center I have the pleasure to direct and this place. We are also quite a large center embedded in an academic campus. In fact, you can see here, one thing you don't have is the lake. One thing we don't have, and I have been fighting for it, but not successfully yet, is the bridge. Because I think the bridge, these are our buildings, and the rest of the campus is across the street, but the bridge is a very important idea. I'm very serious about this. We will see together that also there are very common approaches between the two labs and the common themes. And these would be essentially the examples I will choose. But I like to start from a sort of a general reminder of what we're trying to do in general. If you see the binding energy curve per nucleon that you have in nuclei as a function of atomic number, you can immediately understand that you can gain energy in two ways. You can gain energy if you go from right to left, that is by splitting large nuclei, and that's of course the process of nuclear fission. And you gain quite a bit of energy going down in this curve, so you go down towards the most stable nuclei, iron typically, or you can do the other way around, from left to right, and that is the process of nuclear fusion. So you put together light nuclei, you go down very steeply in a curve, which means per unit mass you gain even much more energy than you do in a nuclear fission. And that's of course the way the stars work. That's the way in fact the universe in a sense was constructed. Now the star put together protons to form a helium nucleus in a chain that takes a long time. We can't afford taking such a long time to make fusion on Earth. You have to explore other reactions. And there's different reactions that we can look at in terms of their probability of happening as a function of temperature or their reactivity as plotted here. And of course, we like to start with the one that's the easiest, that's the most likely to happen for a given temperature. And we identified immediately that as being the deuterium-tritium reaction. So you have the two isotopes of hydrogen that are going to be smashed together to come close enough so that you can really have the nuclear force taking over from the electrostatic repulsion from the positive nuclei, and then turn into a helium nucleus, that is an alpha particle, and a neutron. So this is the blue curve, and that's the one we will be focusing on. But even the blue curve, which is the best of all, needs, in order to have decent reactivity, temperature values that are of the order of tens of keV or tens of millions of degrees. So we are in the presence of a plasma. That's the only matter that can exist in these temperatures. So let's focus on this reaction, which is the one, again, that will give us hope for the first generations of reactors at least. Deuterium, tritium, two isotopes, neutron at 14 MeV, and the energy is very large, which implies also that the material aspects of fusion are very important, and the helium at 3.5 MeV. 3.5 is much more than the temperature with which we'll produce these reactions, which will be in the order of 10 to 20 keV. So this is a very non-thermal particle we need to keep in the plasma in order to self-sustain the reactivity. Now the fuels, deuterium is absolutely no problem, because deuterium is 0.01% of all the hydrogenic atoms in the oceans. The fraction is relatively small, but there are a lot of hydrogenic atoms in the ocean. So 1.6 grams per liter, you can think of an immense amount that's essentially available for us for, I would say, almost infinite time. Tritium does not exist in nature. Tritium is not there for us to take as a fuel, but because it's radioactive and short-lived, it's about 12 years of half-life, but it can be produced from lithium. And lithium can be mined itself, as it is nowadays, or can be extracted from ocean water in decent amounts. It's 0.1 grams per cubic meter. So it's also quite a large amount if you think about the oceans. The reaction we will use is the nuclear reaction between the neutron that's issued by the DT fusion reaction itself and lithium. Maybe I shouldn't go into the details, but it's lithium-6, which is only about 7% of natural lithium, but the cross-section is so large that we don't even need to enrich lithium in order for that to happen in a relatively efficient way. And that reaction produces exactly what we want, that is a tritium nucleus, a triton. In addition, produces an alpha particle and even more energy. And that's what we call the tritium breeding process. Now, that in practice will be performed by what we call a blanket, so something we put around the plasma in which a nuclear reaction will take place. And there are different kinds of technology incarnations of this blanket. This is one example that's developed by our friends at CEA in France. All of them, of course, have to have lithium in it. And the way you actually make it circulate and so on is still not so defined, but research is ongoing. So this blanket around will produce the tritium we need for the reactor. So that means that the fuels, they need to come out. They need to come in your reactor. They need to be bought, if you like, and brought in the plant, are not deuterium and tritium, are deuterium and lithium. These are the primary fuels. So they come in. Deuterium is going to be put in the chamber where the plasma will burn, and lithium will be put in the blanket that will surround the plasma where the nuclear reaction will take place from with the neutron, and that the tritium will be basically be kept in a closed circuit. So what comes in is lithium and deuterium. What comes out is energy in the form of a hot fluid that's created by the neutrons that are captured in the blanket, and a little bit of helium that you produce in your reaction. So that's the schematic of a fusion reactor. We will focus on a magnetic concept, which is based on trapping the particles that are forming the plasma in the cage made of magnetic field. I like to really stress the advantages of fusion, because this is really our core business. Why do we struggle for so long and so intensely to try and achieve fusion? First of all, the energy density you can get in fusion is incredibly high. I like to really quantify that with a quantity that's called specific energy, is number of megajoules per kilograms in your fuel, if you like. If you take water and put it 100 meters high, that's in this amount, in this unit, is 0.001. 0.001 megajoule per kilo. If you burn fossil fuels, coal, oil, or other chemical reactions, if you eat chocolate, as I should, being in Switzerland, or spaghetti, as I should, being Italian, you get tens of megajoule per kilograms, tens. If you go nuclear, then you have 85 millions. So the jump here really makes us understand that the energy density is a completely different game. If you go to fusion, it's even much higher, 350 millions. 350 millions megajoule per kilogram, as opposed to few tens. And that's as close as you can get to actually transform all the mass into energy by just E equals mc squared. That's 90 billion. That's not that far from what fusion can do. So because of that, and because the fuels are distributed around, say in ocean water, we can say they are practically inexhaustible. And the two pictures here I have taken myself in two different parts of the ocean, in two different parts of the planet, also reminds us that this fuel is much better distributed than any other fuel we can think of, except, of course, sunlight. There's no greenhouse gas emission, obviously, there's no combustion, and there's no long-lasting radioactive waste. Why do I specify no long-lasting radioactive waste? Because with the materials that we use at the moment for the structure of the reactor, there will be some activation due to the 14 MeV neutrons that come out. But the activation is limited to the structure of the reactor itself, so it's not going to be released in terms of waste, and it's only lasting some decades with the present choice of materials, and it can be even much less with a smarter choice of materials in the future. It's safe. First of all, there's no link with nuclear weapons. Second, there's no risk of loss of control of the reactions. The concept is not based on the chain reaction, so we cannot, if you lose control of the plasma, if something bad happens to the plasma will terminate, so we'll make a little less money selling electricity, but there will not be a loss of control in terms of safety problems. And at any given time, in the reactor itself, as a kind of exemplified by this picture, we have very, very, very small amount of fuel, just because of this fantastically high energy density. We're talking about grams. In a reactor with grams of fuel that will be burning to produce energy, to produce, power station levels of energy. So I said we trap the plasma, which is made of individual charges, if you like, nuclear and electro-separated, so subject to electromagnetic fields. We trap them in a very sophisticated cage made of magnetic fields, which I will spare you the detail of, but in the present generation, which is in the form of what's called a tokamak, a concept that's based on having fields produced by magnetic coils that will be superconducting in the next generation devices, in some of the present ones, in fact, and currents that actually flow in the plasma itself. The plasma, when it's hot, as it should be, in order to fuse, is almost a perfect conductor, so it's easy to drive a current in it, and that's the idea of the tokamak. So the combination of the external fields produced by the coils and the fields produced by the current in the plasma makes sort of a complicated helical structure for the field, which is optimized to trap the particles of the plasma inside, and in fact the whole plasma in a macroscopic equilibrium in such a situation. So that's a tokamak. And people say sometimes, well, this fusion research takes a long time. Sure, making a star on Earth is not easy, but the progress has been terrific. It's not true that it's been slow. It's been terrific. And the reason I use this graph is exactly to show that. This graph is showing the plasma temperature here as a function of what we call the triple product or fusion performance. It's the amount of plasma you can trap times the confinement time, times the time in which you can trap it, times the temperature at which you trap it. And you can see that, in fact, it was quite easy to jump up in temperature to tens or even 100 millions of degrees quite early. What was more difficult was to push to the right. In other words, to do a plasma, to make a plasma that's hot, but also dense, and also confined for a long time. And we made these jumps. And this is, of course, a scale with exponential here. We made these jumps, and all the way to the last real determined tritium experiments made at the end of the 90s at JET, at the European machine, where we almost got what we call Q of 1, which means the fusion gain of 1. So in other words, almost the same fusion power produced as the power put in. Now, this fusion gain, when it assumes the value of 1, means absolutely nothing except a sort of a psychological barrier. It's called break-even. What counts is when it's bigger than 5 and bigger than 10 and so on. And why? Because if you think of what the plasma does when it's really making reactions, that is heated by the alpha particles, which are one of the two products of the reaction. The alpha particles carry about 1/5 of the fusion reaction energy, 1/5 of the power on average. And if you calculate the fraction of the heating that comes from themselves, in other words, the sort of self-heating of the plasma, as divided by the total heating of the plasma, that's about Q divided by Q plus 5, okay? That's a little bit of algebra, which means that the real game changer will be when you have a gain that's larger than 5, because at that time you have self-heating of the plasma will dominate over what you can do from outside. That's what we call a burning plasma. We don't have that yet. We need to work towards that, and that's the regime in which we will be making power from fusion. Q equals 5 is just, of course, the barrier between, or the kind of mathematical limit between being dominated by external heating and between dominated by internal heating. So we need to go higher than that. And that's exactly what we want to do with the next steps of experiments, which I will show you now. And the next one, in fact, is what we're building now, ITER. That will be the first burning plasma that will be created on Earth. And it will demonstrate that we can do it. It will demonstrate that we can do it scientifically, we can do it technologically, and that it is safe. So to burn means to have a gain larger than 5. In fact, to really burn means be of the order of 10, and that's what we want. So the promise to make a Q of 10 in ITER. And not just for small amount of power, but half a gigawatt. So that's sort of almost a power plant level for a macroscopic time, minutes. This is a construction site of ITER. It's quite a gigantic construction. It has been encountering some difficulties, and more recently, I would say we have regained a lot of faith in the project. It's been now dealt with a real project approach that maybe was not all the way present through the project, but now you can see the site growing and changing very fast. So my pictures are becoming obsolete every week, and that's a very good thing. So this is a picture of the machine. You see the size of a person. There would be about 1,000 cubic meter of plasma. That's the volume of a nice villa, immersed in a field of the order of 5 Tesla, and having a current of the order of 15 millions of amperes to create this nice magnetic cage that will trap plasma in. So that's ITER. That's not the end of research, because there will be one step more. We need to demonstrate not only that we can do it safely, but that we can also do it at the level at which commercial feasibility becomes possible. And that step is referred to as demo. You will need to have parameters like a power plant, so gain of order 30 or 40, thermal power of the order of 3 gigawatts, which means electrical power, say, about 1 gigawatt, and it will be steady state. And different options are being explored around the world. The European option is here. You see other countries are looking at different possibilities. China, you can see from the drawing itself, is, of course, pushing even harder than all the others to make it as early as possible. Let me just say a little bit what I think the building blocks are for reaching this regime and maintaining, and there I show some examples. We have to reach the conditions in which the plasma will burn, which means we have to heat it. That's not so difficult, although we have to heat it at a high density and without spoiling the confinement. We need to control somehow the transport, the turbulence that tends to kick out the energy and the particles. And once we get the burning condition, we need to sustain them. So we need to really take care of this self-heating process in the plasma, keep the plasma stable, and control it in the presence of this very large population of alpha particles, which we don't have today. And also we need to make sure that the burning conditions are not just nice for physics, but they are compatible with reactor operation, which means, first of all, we can exhaust the power and the particles in an efficient way, and second of all, we can actually maintain the walls of the machine in a decent state for a long time. And we have to really also see the implications for the proper reactor operations and economy for fusions, like breeding the tritium and burning up in an efficient way, and having a good thermodynamical efficiency of our plant. I show some examples of how to sustain the burning conditions first, and I remind you again that the fusion reaction is this tritium, and this plasma self-heating comes from the alpha particles. A long way to slow down by giving the energy from 3.5 MeV to 15 keV, and that's about seconds. It's not milliseconds in a big machine like ITER. So during those seconds, there are many interactions that the alphas can have. I show you one example that will also lead to some of the studies we do both in Lausanne and you do here in Holland. The ions can be lost due to a variety of things. This is an example of when they can be ejected from the core of the plasma because of some macroscopic instability in the core of the plasma. This plasma is sort of oscillating up and down, up and down, up and down in its pressure or in its temperature. And when you have this oscillation, you have a build-up of the performance in a core. That's nice. But then you have a collapse. And that collapse kicks things out, kicks the plasma out, and it kicks the fast ions out. So the fast ions in turn influence this instability that would lead to these repetitive collapses. And in particular, it influences the period over which the instability occurs. And the fast ions can make it longer. And if you make it longer, you're happy for a while because you can build up your pressure, so you build up your performance. But the longer you make it, the more violent will be your collapse. So you have to compromise between the length of your good performance phase and the dramatic aspect of the collapse. And you had to play with control of the fast ions and of these instabilities to make an optimal choice between these two things. Also, once the collapse happens, not only do you have particles that are kicked out, but this fact of being kicked out triggers other instabilities that are just about ready to be kicked in your plasma. The plasma is a source of many instabilities because it has a lot of thermodynamical potential, a lot of strong gradients, and so on. So we need to control the period of this instability here, and maybe even control the resulting instability that you can have if you have collapses. So let's see how we do it. This is an example of a tokamak that we have today. It's the tokamak we have in Lausanne. It's called the TCV, tokamak, a variable configuration, which is illustrated by these many shapes we can make in the plasma. And you can see that this is beautiful, but it's also very interesting because the different shapes have different properties for transport, for stability, and even for interactions between the plasma and the wall. But you can also imagine this as a challenge for control. And in fact, in many cases, we came to you guys and say, well, there's a very interesting laboratory for plasma control and for control in general, and that's where plasma physics and control technology actually match. And that's also where our two labs really collaborated, one of the examples. The other specificity we have is that we have quite a large electron cyclotron power, which means the power of microwave that resonate with the motion of the electrons. And recently, in fact, in these very days, we're also installing beams to heat the ions. And these are the different lines with which we carry the waves to heat the plasma. This is an example of an experiment run, in fact, by your personnel on our facility, in which we are controlling the waves we inject in the core of the plasma to, in fact, determine the period of this oscillation I was showing you. And this period, as you see, is controlled in a very systematic and precise way by modulating the power of the microwaves that you inject in the core of the plasma. By controlling the period, you can control the height of the crashes, and you can control also the secondary instability. Speaking of secondary instability, this is another example. In fact, this very simulation came from students of yours who came to do a PhD thesis with us, again, marrying plasma physics and control, and now it's back in Holland, I guess, as a faculty member, and he still collaborates a lot with us. So this is an instability that's generated by a collapse. It's a consequence of the collapse. It's a bubble in the plasma that rotates. It's terrible because it flattens your profile, and if it flattens your profile, you lose performance in the core. So you lose 30–40% of performance in the core, 30–40% of fusion energy in the core. That's a lot. What do you do? Well, the idea is to go and surgically remove it by injecting a microwave beam just at the right location, just at the right time where the bubble is developing. And that's not just a cartoon, that's a reality. It's a simulation based on real data. And that happens, that works. So we've done it, and you need to do it in a in a clever, controlled way, but it works. Now, because it works, it will be transformed from a university academic environment, a nice little PhD thesis, into ITER. Now, this the way we do it in TCV. It's a mirror this big. It's about 15 kilos. It's moved in real time to look and to zap the instability when it's about to grow. And ITER says, okay, that's a great idea, let's do it for ITER. Now, instead of being a 15 kilos object, it's a 20,000 kilos object to inject the beam in ITER. And that's how, it's also an example of how you can kind of extract a basic principle from a relatively small experiment and extrapolate it to a nuclear environment like ITER. Now, we do that in a consortium with many people and across Europe. But that's really something that's happening, and this is one of the approaches we have in common, I think. Now, the second aspect of extrapolating this technique to ITER is to have to really be clever and detecting the mode, regardless of the precision you can have of your detection system and your injection. So one of the ideas that came from here is to detect and inject along the same line, so you don't have problem of absolute mistakes, absolute errors in the position of the mode, with respect to the position of the injection of your beam. And another point is that you can do this in a clever way, again, marrying control ideas with plasma physics, having a model predictive control for optimizing the whole discharge trajectory. So not just taking measurements and transforming them into actuator in a blind or in a very simple way, but having in between a plasma simulation code that tells you where the discharge is evolving, so you can really in real time adapt your control system to make the clever choice. This is one of the things that we developed together, and it's called the Raptor code. It's being used all across Europe to do this kind of a very clever optimization of the discharge trajectory. Another example I'd like to mention is has to do with the compatibility of the burning conditions with reactor operation. The exhaust of power and particles is something that's very crucial, and of course, the interaction between this plasma and the wall is also very crucial. The first wall of our machine has to exhaust the heat and the particles, as I said, but it has to keep the plasma pure, otherwise the plasma will not perform as it should for fusion. It has to minimize the retention of tritium. These grams we put in have to be in the plasma, not in the walls. It has to provide containment of vacuum, and it also has to allow the fueling of the core of the plasma. Now, when we speak of the loading of the wall, we have extreme conditions. Let's compare them with what we have in mind from different systems. A fission reactor, typically, or a turbine for an airplane, or even a spacecraft when it enters the atmosphere, it has of the order 1 megawatt per square meter as thermal loading. The nose of the space shuttle may be a couple, maybe 2, maybe 3, but nothing like 10. We have 10 megawatt per square meter in the critical regions of our reactor in ITER. The launching of a rocket reaches more, reaches about 80, but only for, of course, a very short time. So we are in extreme conditions. And ITER knows that. ITER has to deal with that, and the choice of materials has been made for ITER. The divertor will be made, which is the region where we get most of the heat out, will be made of tungsten, which is good because it has low retention of tritium and it has a high threshold for sputtering. The walls around will be made of beryllium, which has similar properties and low Z, and also pumps high oxygen pretty well. We also have to choose the materials so that we don't deteriorate their properties, thermic and mechanical, under the strong neutron irradiation that we have. Now, what are the challenges? In addition to the steady state loading of power, we also have very violent instabilities. Like you have kind of the surface of the stars, if you like, because you have very large gradients, maybe the largest gradients you can think of in pressure in the whole universe. Over a few millimeters, we go from, hotter than the center of the sun to essentially room temperature. And these generate very violent modes that give you bursts of energy and particles. And in ITER, we have gigawatts for square meter in these ejections, which of course is intolerable. So we need to think about what to do there. We also need to think about what the plasma does there in these conditions and what the materials will become under those fluxes of plasmas. And this is one of the things that's actually being explored here. And I think it's fair to say this is a really unique facility for studying these things, for studying plasma wall interaction. The idea is not to make a huge tokamak to look at the effect of the plasma. Why do you need that? We need here just a very focused plasma that goes on a target with the same kind of power loading that you expect, not only in normal operation, but also during these violent instabilities you will anticipate, unfortunately, may happen in ITER and in even further the other reactor. This is Magnum PSI, which I have just seen downstairs. And these are examples. This is one example of a simulation of one of these events that we fear in ITER and in a reactor for a power loading of the material surface with, in this case, more than 1 gigawatt per square meter, and with a repetition rate 100 hertz, which is also something that we need to look at. So we can look in this kind of machine at the effects of the plasma on the material surfaces without having a complex tokamak around. Now, we're also looking at possible new ways of dealing with the interaction between the plasma and the walls by having different configurations that surround the plasma, in particular different magnetic configuration, because the material limits will not only be approached like in ITER, but will be exceeded in machines after ITER. So we need to do something. We must do something. We cannot just go on and hope the materials by miracle will tolerate more than 10 or 20 megawatt per square meter. So what can we do? We can think of different configurations. For example, we can also think even more in a more revolutionary way that we can have liquid metals flowing instead of actual wall, liquid metals flowing along a small thin layer. And this is something that's being investigated here. We don't do that in our home lab, but this is something that's being investigated here. Or we can think of a very clever configuration for the magnetic edge field that extracts the energy out and that alleviates this problem of the power loading. And these are examples of these two examples of these kind of configurations of the details of the magnetic structure at the edge. I won't go into the details of, but I will mention that one of these two is so-called snowflake divertor, has been pioneered in Lausanne. And on this snowflake divertor, which implies simply having more legs in your magnetic field expansion than the usual divertor, there's a lot of studying being made together with your teams. I skipped this. For the properties that you can have, and if the potential is there, we really to go and extrapolate the reactor. Now, one of the things we will do in the future, the near future, is to have an installation of a real chamber in the machine to create the divertor chamber, divertor area, divertor volume, where the plasma can radiate more, the neutrals will be more dense, so that you can create a cushion between the plasma and the walls and explore that in a variable the configurations that you can optimize the concept. So this is, again, an example where you can do in a relatively simple academic environment, but that can have potential for future machines. We will also use some high-temperature superconducting coils as a demonstration technology for the fission. We collaborate a lot on these points with the teams here. And this is a kind of a summary of what the specificities of a burning plasma can be. And it's complicated because the purpose of the study is actually to be complicated and to say, not only can we try to control things from outside with all different actuators, we need to drive the current in the plasma, we need to fuel the plasma, we need to pump, we need to inject power to heat, we need to make it rotate if we can, but the plasma will be heating itself from inside. The plasma will be dominated by the power from the alpha particles, and that will be sort of self-organized by the plasma itself. It would be difficult to affect entirely what happens in the plasma in a burning plasma, in a burning regime. So all of this coupling is due to these properties of the alpha particles that will be dominating the heating. So there will be transport that would be related to the profiles, that will be related to the heating, which will be related to where the fusion reaction takes place, and so on and so forth. What we can do from outside is to be as smart as we can, to control the different aspects and maybe not entirely control the plasma when we will burn, but in fact kick it in one state or the other that would be beneficial for the operation of the reactor. And that is something that we really are working on together. So there are these blocks. I've seen some examples. We've seen some examples together. Progress must be achieved on these separate blocks. And in fact, I believe Differ really provides an outstanding example of how these different problems are isolated and then address them one by one in depth. So when I discuss, with my colleagues what to do, it's always a good example. We need to understand. I mean, the good people not only are good at answering questions, but they're really good at identifying the question. And you are, I think, a very good example. And we are really working together on some of these questions. So we have to do that. We have to separate the building blocks, and we have to understand the individual phenomena, if you like, as much as possible. But at the same time, in a burning plasma, the coupling of these elements will be essential. It will make extrapolation from what we can do today in only weakly self-heated plasma difficult, and may lead to completely new phenomena. So we need to, at the same time, in our respective labs, address the physics and technology of these individual blocks, but also build the real thing. That is the real burning plasma that will take place, and that's ITER. Thank you very much for your attention.
Okay, well, thank you very much, Ambrogio. Very nice. I guess there are questions. Yeah.
Ambrogio, 2 weeks ago, the fusion was on the cover page of Time magazine. And probably you read the article. So they first of all criticized the fact that all the effort, all the money goes to one configuration, the tokamak. And then it was about private initiatives and small companies mainly in the United States and Canada and one in the UK, using alternative configurations. So do you think these initiatives make sense? Can they really help to reach fusion at an earlier state?
Yes. First of all, they're not all on the same scientific level, should I say. Some of them have claims that are totally, let's say, exaggerated. Some others have taken a very sound approach. I think it's great for fusion that people trying different things, that people are trying to go as fast as possible. Again, some of the private investors are investing in concepts that maybe are significantly behind the concept of the tokamak. We'll see. Maybe they will one day reach the development level that we have. It's not true that the entire funding on fusion, the public funding on fusion, is spent on tokamak. There are significant investment in what's called a stellarator, which is a slightly different way of making this magnetic cage. And the biggest stellarator ever is about to open in Greifswald in north of Germany. But I more than welcome all of the initiatives from private, of course, to have alternative approaches, faster fusion and so on, as long as they don't kind of criticize in a non-scientific way what mainstream is. First of all, for example, if you want to have a fusion reactor based on DT, which I think is most reasonable, you have to have a blanket that produces tritium. And when people say, I can do a tabletop device, they just have not looked at the neutronics 101. In neutrons cross-section, there's not much you can do about. They are the way they are. So you need about a meter to slow down a neutron, breed tritium, and screen and shield. So, my point is that demo should not be bigger than ITER. But if you tell me they will be this big, I just don't believe you. It's because of cross-sections of neutrons. Okay, now the people say, well, we don't do neutrons, we do proton-boron reactions. But then you have cross-sections that are so small that you need to go to 400 millions of degrees, and then you have to tell me how you confine the plasma at those temperatures and so on. So all the approaches are possible. I was, in fact, in an event with the students in Prague yesterday and the day before yesterday, and I met the person from ITER, and she told me that they opened up the possibility of a private sponsorship of ITER, which is of parts of ITER. And of course, at the moment, it's only in the form of grants for students and scientists and so on, but I think it's a fantastic opening, which I actually didn't expect, at least in the previous management of ITER. I asked the question, the answer was just a laugh, which I thought was a bit unfair, but why not? So it's happening in Europe as well.
Okay, I have to make very short huishoudelijke mededeling. There will be another lab tour starting in a few minutes. So if you want to go to the lab tour, I think you have to leave the discussion now. We will continue this discussion for another few minutes. So, are there other questions? Yeah?
You showed there are several initiatives worldwide in one of your first slides. Which part of the big challenges is tackled in a global effort, and where are scientists and engineers actually competing for the different designs or approaches? Can you comment on that?
No, ITER is a global effort, and it is a sort of it's pro and it's con at the same time. It was built as a peaceful global effort, initially from Reagan and Gorbachev, blah, 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 with the idea that the technology and know-how will be built in parallel in all the participants, which of course is not the most effective way of proceeding, but is the most effective way if the end goal is to have all of them at the same level. So ITER is a global effort, and things are provided in kind by different participants, which is not easy, but maybe that's why it's taking a little longer. But it's a way that people actually develop their know-how. So ITER is really a collaborative effort. Not all the world is in ITER, but almost.
But the other...
And the step after that, I think it would be, in my opinion, if ITER really works as it should be, then it would be more than one device.
So Korea, Japan, etc., they built on ITER rather than having some kind of parallel developments?
They are going almost in parallel. We in Europe, we also try to go partly in parallel with ITER, in a sense that the step after it will not wait at the end of ITER, otherwise it would be too late. And of course, the Chinese are saying, well, we will go even earlier, but it will be based on what we learn, at least from the initial phase of ITER. There could be different approaches. The Americans are now pushing for a high-temperature superconducting machine. Again, it made the first page of something, or I don't know, in the New York Times or something. But it's easy to say. One thing is to make a tape of superconducting, high-temperature superconducting. One thing is to make a magnet that has, 1,000 cubic meter of volume at 10 Tesla, and a lot of stress. So I think we have to build that up also.
Thank you.
Thank you.
There was another question here, I think. Yeah, Dan?
Do we understand that this release of energy is the main challenge?
The what?
The release of energy.
The release, the exhaust.
Like sawtooth.
It's one of the main challenges, yes.
Is it something you can influence on a positive way? Let's say that you force the system to release. That you also can not wait and see how it develops, but that you imply a system in which you force the release of energy.
Well, the problem is not that the energy is not coming out. The problem is the energy is coming out on surfaces that are not withstanding the power load. So, and at the same time, we don't want to make the machine too big, because of course that could be a relatively simple solution. In fact, it's not that simple even, because it turns out that if you increase the machine, you only gain with the linear size of the machine and not with the square, as you would imagine, because the power is concentrated because of plasma physics at the edge on a particular thin layer. So you gain with R, not with R square, which is a very, very pathetic gain, in fact, if you make it bigger. So the power is coming out, and we're trying to optimize the way it's coming out. For example, we would like it to be radiated by the layer at the edge as opposed to being convected or conducted by the plasma, because if it's radiated, it's isotropically radiated, and it's much better than just going on a particular spot. So we're trying to combine this regime. Now we can do that. We can radiate the power, but we have to do it, and that's one of the interdisciplinarity of plasma, if you like. We have to do it compatibly with the optimized operation of the core. Core must be pure, must be super well confined. The edge must be radiating all the power before the plasma gets to the wall. And these two things are not easy to combine.
I guess there's room for one last question. If not, I suggest we thank Ambrogio again.
Thank you.
Ambrogio, as a token of our appreciation. Thank you very much.
Thank you very much. Thank you.
Okay. Have a good one.